In this video, we're going to be looking at some notational conventions of arbitrary families of sets. To get started, I want to let S be a set, and we're going to refer to S as the index set. And for each X inside set S, we want to define or specify a set that is simply going to be called A sub X. And we call the family, and the family is going to be written as script capital F, the family of the collection of A sub X's such that X belongs to S, an arbitrary collection of sets indexed by the set S. And it's important to note that if S is uncountable, then we cannot use the natural numbers to denote the elements, or rather the sets, in our family. And that's one of the reasons that we need this kind of notation, is that we can have uncountable families of sets. I would like to actually look at an example of an uncountable family of sets. So as an example, I want to let my indexing set be the closed interval between 0 and 1. And this is all the real numbers such that X is between 0 and 1 inclusive. And for each X inside that interval, I'm going to define the set AX to be the the open interval between minus X and, let's say, 2 minus X. Let's clean up my notation there, 2 minus X. And all I really want to do right now is I want to look at examples of members of this uncountable family of sets. And I know it's an uncountable family because intervals of real numbers are uncountable. Well, I'm simply going to kind of pick different values of different elements of S and look at their corresponding sets. 0 is inside this interval, and A sub 0 would be the interval between minus 0 and 2 minus 0, so that would be the open interval between 0 and 2. 1 certainly belongs to this particular interval, so A sub 1 would be minus 1 to 2 minus 1. In other words, it's the open interval between minus 1 and positive 1. But we have lots of other, those are the only integers that live inside my indexing set. But we have lots of other numbers inside the indexing set. 1/2 belongs to that indexing set, and A sub 1/2 would be the open interval between minus 1/2 and 2 minus 1/2. In other words, this would be the open interval between minus 1/2 and 3/2. Let's see, 2/3 belongs to this indexing set, so A sub 2/3 would be the open interval between minus 2/3 and 2 minus 2/3, and 2 minus 2/3 is 4/3. So A sub 2/3 would be the open interval between minus 2/3 and positive 2/3. But we have other irrational elements inside this set as well. 1 over the square root of 2 lives inside that particular set, and A sub 1 over the square root of 2 would be the open interval between minus 1 over root 2 and 2 minus 1 over root 2. Let's see, 1 over pi is another irrational number inside this particular set, and the corresponding set inside the family would be 1 over, would be a sub 1 over pi, and that would be the open interval between minus 1 over pi and 2 minus 1 over pi. So that gives you an idea of how this indexing works. We would have an infinite, well, we'd have more than an infinite number. We'd have an uncountable number of possible subscripts in this family, and the whole family is uncountable, but each and every one of the elements in the family is quite understandable. Well, one of the reasons that we want to do this kind of thing is that we can talk about unions and intersections of arbitrary families. So if I have an arbitrary family of sets where every member of the family is an a sub x, where x belongs to some indexing set named S, we can talk about the union of all of the members of F. We can talk about the intersection of all of the members of F. But we need some decent notation for describing those things, as well as a precise set theoretical definition. So if I think in terms of the union of the sets in F, I'm going to want to write that as a big union sign, and it's going to be the union over all of the S's inside my indexing set S of the corresponding sets. So we would be writing this as the union of the A sub x's where x runs through all of S. Now what would this set be? Well, it would be the set of A's such that there exists an Sx inside my indexing set S such that little a belongs to set capital A sub x. In other words, y belongs to this union if and only if there exists an a sub x inside my family with a belonging to that member of the family. So that's really what the unions mean, and it turns out that this kind of awkward notation is really the best notation that we can have to describe a union of an arbitrary number of sets. Intersections work the same way. If I want to think about the intersection of all of the things inside my family, that's going to be written as the intersection of the a sub x's, where x runs through the whole indexing set, and that is going to be defined as all of the a's such that for every x inside S, a belongs to a sub x. In other words, y belongs to the intersection of the a sub x's as x runs through all of the indexing set is going to happen if and only if y belongs to a sub x for all of the members of my family. So unions and intersections are done in exactly the same way that they would always be done. It's just that we wind up using this slightly more general definition of how to do the symbols.